Hello and welcome to this video on what is a solid state weld. To begin with, let me start by sharing my screen so you can follow along with the PowerPoint that I'm going to use. My name is Girish Kelkar and I am a welding consultant operating as WJM Technologies. Additional information about my consulting business is on the web at welding-consultant.com, and you're going to find this video on my YouTube channel at Weld Nugget. So what exactly is a solid state weld? For that, let's start by looking at what are the different types of bonding and joining techniques that we have. The four ones we list over here are solder. Soldering is a low temperature bonding process where we have a solder alloy which melts and bonds with the two components, usually for electrical connections. Brazing is similar to soldering, except that the filler alloy that we add is a higher melting point alloy, but the base metals still do not melt. Fusion welding is perhaps the most well-known in terms of welding, and that includes laser welding, TIG, MIG, plasma, and so on. And fusion welding, as the name implies, produces a fusion between the two parts being joined, and you might be actually adding a third alloy in there as well. The fourth one is the solid state bond or a solid state weld. And that includes friction, ultrasonic, resistance welding, and many others. But solid state bond or weld is perhaps the most misunderstood of exactly how this bond actually forms at the interface. To understand that, we are going to first look at what is a metallic bond. A metallic bond is a bond which can form between two metal atoms just because they are in very close proximity. Here I'm showing you a schematic of two metal atoms. Each atom has a nuclei which is positively charged and a electron cloud which is floating around on the outside which is negatively charged. When you bring two metal atoms together, the nuclei on either side also attracts the electron cloud on the other atom, and that is what produces what is called a metallic bond. Now, this bond is a bit different than ionic bond that you might have heard about. It's in sodium chloride. So salts have an ionic bond, which includes an exchange of electrons between the atoms, or a covalent bond, which is a directional bond between two neighboring atoms. But metallic bond does not do any of that. All it depends on is attraction between the nuclei on one side and the electron cloud on the other. And this can be for multiple atoms. So if you add 3 or 4 atoms, they will all huddle together to form a glob. What happens when you have multiple atoms? In reality, of course, we are going to be dealing with thousands of atoms. If there are multiple atoms, then you will find that these atoms do have a certain preferential orientation in different regions. And these regions over here, and this preferential orientation and arrangement depends on the size of the atom and the electron conductivity on these atoms as well. So different atoms or different metals will have slightly different structures. Now, each grain can be made of the same type of atoms or a mixture. For example, this grain could be pure copper and the neighboring grain could be, say, platinum iridium, for example. Now, these grains come together at this interface called the grain boundary. Now, this border between two grains is known as the grain boundary, where the structure is not as precise as within the grains themselves. So this grain boundary does provide locations for impurities to collect or misfit atoms to collect over there. All the atoms within each grain and across the grain boundaries are still bonded with a metallic bond. So when you cross-section an alloy or a metal or an alloy, which is a mixture of metals essentially, and you polish and find different grains, the atoms within each grain are still bonded with a metallic bond, and across the grain boundary, the two grains are attracted to each other also by the same metallic bond. Now, in this schematic, I'm showing you two grains. In reality, a component might have thousands or millions of grains. So here I'm showing you a cross section of a structure with equiaxed grains. That means the grains have the same approximate dimension in all directions. And here we are showing a structure with elongated grains. That means the grains have been pulled in one direction and they appear like strings. This is in cross section. Now all these grains are bonded to each other with their metallic bond. So these along the grain boundaries and within the grains, the bonding is still a metallic bond. So for example, I'm holding here a piece of strip of aluminum sheet, and this aluminum sheet is likely to have thousands and thousands of grains, and it is still pretty strong. So the grains are not falling apart. It has a certain amount of strength as would be expected from a piece of aluminum. And all of these grains are bonded by this metallic bond. Now, what exactly happens in a solid state weld or a solid state bond, for example? So here I'm showing you a cross section of two components of copper, and you can see the bond line between the two. So this bonding was done with a resistance welding machine. You can see the grains on one side in this piece of copper. You can see the grains on the other side in this piece of copper. So when metal components are brought into close contact, so when we bring two, say in this case, two pieces of copper into close contact and push them together, and we actually create a long, effectively like a grain boundary. So the grains on either side are now being pushed together against grain on the other side, and we form a long grain boundary. Now, the bonding across this boundary is still a metallic bond, and that is essentially what is a solid state weld or a solid state bond. So, the solid state bond or a solid state weld is going to be, when properly made, is going to be as strong as the base metal itself. So, if you take two pieces of copper and make an excellent quality solid state bond, that bond is going to have the same strength as the base metal copper. The most important thing to keep in mind in this whole discussion is that there is no need for a reaction or melting or diffusion to form this solid state bond. So it does not have, these two copper components don't have to react with each other in any way. They don't have to melt, and they do not require atoms to diffuse from one side to the other. And the reason why this misunderstanding is there is because when you make a solid state bond and you test it, the bond is extremely strong. And then a lot of times there is a need to justify this strength. And then there is a need to say, okay, there's something must be happening over there which is different. So there must be some reaction, must be some melting, or must be some diffusion. But that is not true. What you have is a pure metallic bond, which is called a solid state bond. There are many processes which produce such solid state bonds or solid state welds, including friction welding, friction stir welding, ultrasonic welding, resistance welding, explosion welding. Yes, there is a process called explosion welding. And how that works is you take two sheets of metal, and you have an explosive on one side, and you trigger that explosive, and the one sheet is then accelerated onto the other sheet with the extremely high force, and that produces a fantastic solid state bond. Of course, this is not something you want to do in your home or even in a factory. There are very special locations where this is done in a safe environment. Then there is called a magnetic impulse welding, which is kind of like a explosion welding, except that the acceleration is provided by a magnetic coil producing magnetic forces into the components. Then there is roll welding. Literally, you take say you can take two pieces of copper or copper and aluminum and put through heavy rolls and literally pushes the two together and forms a bond. And then there is pressure bonding, which is just as it sounds, or you can call it cold welding. You take, say, thin foils of, say, copper or aluminum or anything, put them in a heavy, heavy press at a very high pressure, hold it for a few seconds or like a minute or less, and you release the pressure and everything is bonded together. Now I'm going to show you some cross sections of such bonds. Here's a cross section of a magnetic impulse welded sample. So here we have two components, one of copper and one of aluminum. And very high forces are created by a magnetic coil, which is outside the copper tube. So the geometry which works with magnetic impulse welding is tube into tube. So there's an outer tube of one material, there's an inner tube of another material, and there's a coil on the outside. And when you energize the coil, the copper is forced onto the inner tube. And this tremendous force, which is applied for a fraction of a second, produces an excellent solid state bond, as you can see from this line over here. Many solid state welding processes are very, very fast, and it just does not have the time required for diffusion. Now, diffusion is a time and temperature dependent process, whereas many of these solid state bonds happen fairly low temperature and very, very fast. And that's why diffusion is not really a component of this bonding process. Now you can create diffusion. So for example, if you take this bond which you have made between copper and aluminum, and it's a very good bond, and you stick it into a furnace at a certain temperature, then copper and aluminum can start migrating into each other if you need to. But it is not necessary. So the bonding is not because of diffusion. The bonding is already there by solid state bonding or solid state welding. And the diffusion, you are just trying to change the chemistry across the interface. Now, that may or may not be a good idea. For example, if you have copper and aluminum and you actually encourage diffusion, then you might actually form reaction products such as copper aluminum intermetallics, which are quite brittle. And you might actually weaken the bond because now we have brittle components at the interface. So oftentimes you actually don't want any interaction or between the two components. So you actually prefer not to have diffusion across the interface. Here's an example of ultrasonic welding. Ultrasonic welding is a process which energizes the metals with ultrasonic energy. Here you can see a cross section of multiple layers of aluminum being bonded to an aluminum component. And each of these layers is of the order of about 25 microns or 1,000th thin foil. And if you look closely, you can see that there is a lot of disturbance between these layers. And as the energy comes down, it actually disturbs these interfaces and produces some amount of mechanical mixing as the energy flows into this weld. The ultrasonic energy actually softens the metal, and in that process, with the application of force, actually breaks the oxide film. So aluminum has a thin, naturally oxide film on the surface, but you don't need to remove that film completely. A very thin, naturally occurring oxide is acceptable for ultrasonic welding because the ultrasonic energy softens the metal, and when you push it, it actually breaks, changes the shape of the foil locally, breaks the oxide film, and exposes fresh metal on either side to form a bond. So there is some amount of mechanical mixing at the interface. As you can see that the interface looks disturbed. Whereas in the previous example I had shown, the interface is very clean and a single line for magnetic impulse welding, and same for resistance welding when those two processes form a ultrasonic weld, solid state weld. But in ultrasonic welding, you do have some amount of disturbance. And that is true with other processes as well. For example, friction stir welding of aluminum alloys. When you do friction stir welding of aluminum alloys, you actually, without producing fusion, but you produce a lot of mechanical mixing. So one of the key aspects of friction stir welding is the mechanical mixing. The friction welding itself does not produce that much any mixing at all. But friction stir welding produces a lot of mixing. So here you can see the two aluminum alloys. Based on the etching, you can tell that they were different alloy compositions, and you can see a lot of mixing between the two over here. This would have been otherwise a straight line at the interface before the weld was made, and now you can see a lot of mixing. Now, friction stir welding is commonly done for butt welding two components, but this is a unique application where the friction stir welding was done for a lap welding application, which is quite unique. So what are the pros and cons of a solid state weld or a solid state bond? The most important one is a strong bond with no interaction. allows welding of dissimilar materials. So there are a lot of applications where you want two metals to join together, but without having an interaction, because any interaction will produce, say, a brittle interlayer, brittle interface, which can weaken the bond. And that is pretty true with pretty much any dissimilar material welding. So, for example, copper to aluminum or iron to titanium, anything you do oftentimes will produce some amount of intermetallic formation. And these processes, because they are very fast and room temperature, they do not produce any significant amount of temperature or close to room temperature, let's say. They do not produce a lot of temperature, and they don't have enough time for diffusion. So that is why this type of bond is excellent if you do not want to have the materials mix. Now, it's not necessary. It's not necessary. For example, here I showed you an example of a copper to copper bond where you could have interaction because there won't be any interaction, just copper to copper. But still, for that particular application, a solid state bond proves to be easier. Same with over here. This is aluminum to aluminum. It is between similar materials and still is a useful application for solid state welding. This is a good example of dissimilar materials where you would not want them to react too much. And we have formed a good solid state bond. The temperatures are lower than a fusion bond, and that is important because at a lower temperature, when you go up to a lower temperature, then you come down from that to room temperature, you have less stress in the weld. So there are a lot of benefits about solid state welding. The cons are essentially you do require a suitable geometry. So not all geometries are adaptable to solid state welding. So you do require geometries which have good contact area between the two components. So oftentimes, essentially, it becomes a lap weld or a butt weld within two thick components. You do require a lot of force. So obviously, you need a machine which can apply that much force. And you do require the parts to be clean, relatively clean of oils and contaminants. It doesn't have to be atomic level clean or microscopically clean, but clean enough in normal operating conditions. And there's some amount of cleaning does occur during welding. So there's some amount of heating in some processes, some amount of pushing out of the intermediate contaminants in some processes. So there is some amount of cleaning action during welding, but ideally you want very clean components before they are brought to for the joining process. It does require parts to be free of oxide. So again, here you do not want specially grown oxide layers on the surface. For example, aluminum. Now, aluminum, a naturally occurring aluminum, is bright and shiny. It is going to have some amount of oxide, but that is acceptable. But there are some applications where you have anodized the aluminum to grow a special thicker layer of oxide, and that is not acceptable for solid state welding. So there are certain restrictions, but there are also some pros and over here. And consequently, it is a very popular process or popular way of bonding. And that includes many processes in solid state welding, such as friction welding, friction stir, ultrasonic. So you might have heard of many of these, and some of these might be new, and they are very applicable in unique situations. In summary, solid state bond is one of the three commonly formed bonds when joining metals. The other two are solder and braze. Solder and braze, I lump them together because in a sense they are similar because you're adding something in between without allowing the base metal to melt. And the third one is fusion welding. So we have three different ways of forming a good metallurgical bond: solid state welding or bonding, solder and braze, and fusion welding. Solid state bond essentially forms by an atom to atom interaction between the metals and does not require any type of reaction, melting, or diffusion. Now, this is very, very important to realize that it is not required. There's no reaction, expectation of a reaction, melting, or diffusion at the interface, and you still form a very strong bond. Now, that comes as a surprise to a lot of people, even in the welding business, because intuitively you would think that if the bond is strong, then something must have happened at the interface. And all that has happened is you have brought metal atoms on both sides into intimate contact, without having any contaminants or oxides or anything between, and they will form a bond, which is the solid state bond. Solid state bond has the benefit of the ability to join dissimilar materials that would otherwise react in fusion welding. So a lot of metals actually are hard to weld to each other because they would otherwise react. So only way to bond them together, one of the ways, say, is solid state welding. The other ways are, say, soldering or brazing, but then you introduce a third component in there whose properties may not be acceptable for the application of the bond. So you can form a bond between, say, aluminum and steel, and that is done by explosion welding. You can bond copper to aluminum by ultrasonic welding or magnetic impulse welding, or of course, explosion welding. And there are many such applications where solid state bond comes into play. One of the limitations of solid state bond is does require a special geometry. For example, you have to be able to push the parts together, and does require parts to be relatively clean and do require application of a high mechanical force. So that is why solid state bonding is very difficult to do with a manual process. So usually it requires some very sturdy and strong machine and certain amount of part preparation and cleanliness. But nonetheless, it is these processes are very commonly used and form a very strong bond without having any kind of melting or reaction or diffusion. If you're interested in learning more about welding and joining, please subscribe to this YouTube channel by clicking the subscribe button below. And on this YouTube channel, you will find many videos in different playlists, including laser welding, arc welding, resistance welding, other welding processes, welding metallurgy, and weld design. I want to thank you for your time and your patience in listening to this video and watching this video. I want to wish you the best in learning more about welding, and take care.